The hyperbola. In this video, we give a geometric definition of a hyperbola, and we investigate the geometric properties of hyperbolas to obtain an equation. By the way, if you like this video, don't forget to like and subscribe to this channel and activate the bell. It's very important for the continuity of this channel. A hyperbola is a conic section formed by intersecting a right circular cone with a plane at an angle such that both halves of the cone are intersected. This intersection produces two separate curves that are mirror images of each other. Although each branch might look like a parabola, its shape is actually quite different. The definition, features, and derivation of a hyperbola closely resemble those for an ellipse. It's very helpful to compare the nature of the hyperbola with the nature of the ellipse. Although ellipses and hyperbolas have completely different shapes, their definitions and equations are similar. Instead of using the sum of distance from two fixed foci, as in the case of an ellipse, we use the difference to define a hyperbola. Geometric definition of hyperbola. A hyperbola is the set of points in a plane such that the difference of the distance of each point from two fixed points, called the foci, is constant. Each fixed point is called a focus, and the point midway between the foci is called the center. The line containing the foci is the transverse axis or focal axis. The line through the center and perpendicular to the transverse axis is the conjugate axis. The transverse axis intersects the hyperbola at 2 points, called the vertices, and the absolute value of the difference of the distance from two fixed points, called the foci, is constant. Now we can derive the simplest equation of a hyperbola by placing the hyperbola centered at the origin with its focal axis on the x-axis. The distance from the center to a vertex of a hyperbola is a units. The distance from the center to a focus is c units. So the vertices are at minus a and 0, and a and 0, and the foci are at minus c and 0, and c and 0. The distance between the vertices is 2 times a. From the definition of a hyperbola, we know that the difference of the distance from any point on the hyperbola to the foci is a constant distance. We now will find the constant distance. Let P be a point on the hyperbola. We place the point P on the vertex that is on the left-hand branch. Let D1 be the distance from the focus that is on the left-hand branch to the vertex. D1 is minus A minus C. Let D2 be the distance from the focus that is on the right-hand branch to the vertex. D2 is C minus A. As we can see, D1 minus D2 is 2 times A. This equation is very important to get the equation of a hyperbola. The difference of the distance from any point on the hyperbola to the foci is 2 times A or minus 2 times A units, depending on the order in which you subtract. Before deriving the equation of the hyperbola, we are going to seek for an expression that relates the values of a and c as we did for ellipses. We begin for drawing two vertical lines through the vertices. Then we draw a circle centered at the origin and passing through the foci. We can see that the radius equals c. The distance between the vertex and the point that the vertical line intersects the circle is b. We now can use the Pythagorean theorem to relate the values a, b, and c. At last, as a helpful tool for graphing hyperbolas, it's common to draw a central rectangle as a guide. This is a rectangle drawn around the center with sides parallel to the coordinate axes that pass through each vertex. We now apply the Pythagorean theorem to the right triangle to obtain the Pythagorean relation for hyperbolas. From the definition of a hyperbola, we will find an equation of a hyperbola centered at the origin, opening horizontally with foci at c0 and minus c and 0. Use the distance formula. After eliminating radicals and simplifying, we obtained the standard form of the equation of a hyperbola centered at the origin. Pay attention. This is the standard form of the equation of a hyperbola centered at the origin. At last, as a helpful tool for graphing hyperbolas, it's common to draw a central rectangle as a guide. Begin by plotting the vertices, and then plot the points 0 and minus b, and 0 and b. We now use these 4 points to construct a rectangle. The diagonals of this rectangle have slopes b over a and minus b over a, and their extensions are the asymptotes of the hyperbola. If we graph the asymptotes, we can use them to establish the opening of the hyperbola and avoid plotting other points. If a hyperbola with center at the origin and transverse axis coinciding with a coordinate axis is shifted horizontally h units and then vertically k units, the result is a hyperbola with center at hk. Horizontal and vertical translations are accomplished by replacing x with x minus h and y with y minus k in the standard form of the hyperbolas equation. Therefore, applying shifts to hyperbolas leads to the following equations. Table below gives the standard forms of equations of hyperbolas centered at hk and shows their graphs. Let's see how it works. First, we locate the foci and the vertices in the Cartesian plane. We need to identify the center, hk. The center is halfway between the vertices. By the midpoint formula, the center of the hyperbola occurs at the point 3 minus 2. We can see that the hyperbola has a horizontal transverse axis, and the standard form of the equation is To find the value of A, we should remember that A is the distance from the center to vertex. And to find the value of C, we should remember that C is the distance from the center to focus. We now find the value of B. So the equation we seek is given as follows. To help us sketch the hyperbola, we draw the central rectangle by plotting the points 3 minus 2 plus 4 and 3 minus 2 minus 4. We then draw the asymptotes and complete the graph of the hyperbola. Let's see another example. We begin by writing the equation in standard form. The right side should be 1, so we divide both sides by the constant term to place the equation in standard form. Simplify. The right side is now 1. From this equation, we can conclude that the hyperbola has a vertical transverse axis, based on the standard form of the equation with the transverse axis on the y-axis. This vertical hyperbola, with its center at the origin, has vertices at 0, 2 and 0, minus 2. The value of B is 3. We can find the value of C. The foci are at 0 square root of 5 and 0 minus square root of 5. We now locate the foci in the vertices in the Cartesian plane. We draw the central rectangle by plotting the points 0, minus 3 and 0, 3. We then draw the asymptotes and complete the graph of the hyperbola. Let's see another example. The vertices are at 3, 1, and 3 and minus 5. The center is the midpoint of the segment connecting the vertices. Or 3 and minus 2. The value of A is the distance from the center to a vertex, or 3 units. From the asymptotes, we can find the slopes and then the value of B. The slope is 2, but we know this slope is A over B as well. So we can find the value of B. The standard equation of this hyperbola is the equations of the asymptotes are given as follows. If we wish, we can find the foci as well.